All right, ninth graders, we are going to do the second part of the Newton's third law worksheet here. And starting with number 7, you've got two identical weights hanging by strings connected to a spring scale. And the question is, what does the scale read if each of the weights is 50 newtons? And again, we're talking about Newton's third law here. So what's going on? Well, think of two objects. You've got one object, which is the spring. And I'm not going to draw it as a spring. And I've got the other weight here. And because of the way the pulley changes the direction here, the spring is pulling on the weight here with a force of 50 newtons. If spring pull on weight, weight pull on spring, also with 50 newtons, and that's going to show that 50 newtons are being pulled on the spring. Why not 100? What's this weight doing? That weight basically is just making it so that this isn't going to move, all right? So in addition, the whole housing of the spring scale has two forces on it, 50 newtons and 50 newtons. Those are balanced forces. Those are not action-reaction forces, and that means that the spring is not, the whole case and the spring inside it are going to be stationary because they already were stationary. But the reading on the scale is going to read 50. All right, moving on to number 8. All right, here we have a strongman between two railway cars, and he pushes both of them together as he drops to the ground. So he's just going to go down. So the question is, what will happen to the two train cars? And the answer is that, well, again, let's do a free body diagram. All right, this is train car number 1. This is train car number 2. He's pushing, basically, you can kind of think of him and this train car as being connected together, pushing on that car, okay, with some amount of force. But you can think of this train car and that guy being, as one thing, pushing exactly the same amount. The forces have to be equal and opposite, again, because of Newton's third law. If there are no other forces, then they're going to accelerate. And because they have the same mass, their equal mass, they will accelerate at the same rate. Why not a constant speed? Because there would have to be another force pushing back exactly the same amount, and it doesn't mention anything about that. All right, number 9. Suppose two carts, one twice as massive as the other, fly apart when a compressed spring that joins them is released. So here, then it says afterward, how do their speeds compare? So this spring is going to provide the same force. Again, it's pushing off of the twice as massive cart onto this one, but this one it's pushing off of here and pushing on that one. So again, you can think of this as the same force acting on both objects. This is M and this is 2M. All right, so then the question, what we're asking about here is the effect. The forces are the same, all right? But here you've got small mass, big acceleration. Here you've got large mass, smaller acceleration. If you have twice the mass, you're gonna have half the acceleration, which means that it will, the heavier cart is going to be slower. All right, number 10. Two people of equal mass, that's probably important, attempt a tug of war with a 12-meter rope while standing on frictionless ice. So this person is going to get pulled this way, this person is going to get pulled in this direction, and there is no friction, so they're going to actually move in the directions that they're being forced. And again, those forces are the same. So when they pull on the rope, they slide toward each other. How far does each person slide before they meet? Well, if their forces are the same and they have the same masses, then their accelerations are going to be the same, which means they will both move the same distance and they'll meet exactly in the middle. Okay. All right, let's move on to number 11 now. Number 11 is a variation of this problem. And it says, suppose that the preceding example, one person has twice the mass of the other. How far does each person slide before they meet? Okay, so this time you have 2m, and 1m. But again, they're pulling with the same amount of force. So the one with twice the mass is going to have half the acceleration as this person. So this person's going to accelerate more and go faster and be able to go farther. In fact, because their acceleration is twice as much, they're going to go twice as far. So the lighter, heavier person will slide half as much, 4 meters, as the lighter person. Again, there's 12 meters between them. So they will not meet in the middle this time. And that brings us finally to number 12. This is one of my favorite questions with Newton's third law. A horse pulls a wagon with some force, causing it to accelerate. Newton's third law says that the wagon exerts an equal and opposite reaction force on the horse. So how can the wagon move? Okay, this is all correct, but let's take a look at the two different objects. All right, here's the cart and here's the horse. All right, so what forces are acting on each of them? They both have a normal force and a weight, okay? And they may be different. I mean, from the normal forces are different and then the weight forces are different, but nevertheless, they balance out. So they're not going to play much of a part here. Now, it says that the horse pulls on the cart. This is the force of the horse on the cart. Well, if horse pull on cart, then cart pull on horse, exactly same amount. Cart on horse. All right, those forces are equal. So then how do you go anywhere? And the reason for it is there are other forces at play here. What is the horse doing? The horse is pulling on the cart, yes, but the horse is also pushing against the ground. This is the force of horse on earth. All right, well, if horse push on earth, earth push on horse. Okay, and we've got that force right here. Earth on horse. So if the earth is pushing the horse forward more than the cart is pulling it back, then they are going to accelerate. So it's not the wagon has wheels so it can move. Horses can pull plows and sleighs and things that don't have wheels. So we know it's not that. There's less gravity pulling on the wagon. That might be true, but that's not the reason why. See, the horse pulls harder to overcome the reaction force. That is not the case. If the horse pulls harder on the cart will pull harder on the horse. But those forces do not cancel out because they are on different objects. Okay, only forces on the same object can cancel each other out. The reason is there is an unbalanced force on the cart, so it moves. Look at this here. Here is the cart. The only force pulling it is the horse. There's nothing to stop that horizontal force, so it's going to go forward. The horse will go forward too, because this amount of force is not enough to overcome the entire force of the earth on the horse. Now, if you took away the ground here, put the horse on ice, and the horse couldn't gain any traction or have any static friction to be able to push against the earth, then there would not be this force of the earth on the horse because the horse couldn't push on the earth. And then no, they wouldn't go anywhere. All right, that's the end.